One of the best ways that we can optimize our queries is to skip data that we don't need to be using in the queries. And there's a number of different ways that we can implement these data skipping techniques. So with regard to data skipping, essentially what we're wanting to do is we're trying to eliminate the need to open files that do not contain data that we need in our query. And so if we can keep from doing that, we're going to increase the optimization of our query. So we can essentially say, hey, if we need to scan through a bunch of files, open them up and take that process and hey, let's read the data, we don't need it, that's just wasted time. So what can we do? One thing we could do is Z-ordering. Now I can tell you that Databricks right now is recommending liquid clustering as opposed to Z-ordering or partitioning data. But I'm going to talk to you about Z-ordering because there are some times where you might still want to use it. So what we do with Z-ordering is we say, hey, let's go ahead and order the data in a table based on a specific column. And then when we cause that order to happen, we can say, hey, if we are running a filter and that data point doesn't exist inside a specific file, we don't even need to open that file. We can totally just skip it. So for example, we perform Z-order on some column, right? Here's our column min now, the old column min, the old column max. We perform the Z-order, and now we have things in order. We have a specific minimum and maximum, and that'll be placed in the footer of that Parquet file, which will be very helpful. Then when we do, hey, we'll do select star from some table where column equals 7, in the old order, before we perform that Z-order, we're going to be opening these two files to find that 7 in those two files. Where in the new layout, we just open the one file because we know that 7 is going to only exist in that specific file because we've calculated those statistics and we know that these other two files don't contain that value. Now keep in mind though that we need to collect those statistics. Now Databricks Delta Lake has specific statistics that are collected. The default is that the first 32 columns in a table are going to have statistics calculated for them. Now these statistics are going to be used in queries. Right? For example, if we're just doing a metadata only query, right? So if we just do select max with a specific column from our table, then we're just going to query the delta log. We don't even need to look in any of the files that contain that data as long as that column has those statistics calculated on it. This allows us to skip a huge number of files. And keep in mind that our partition filters, our data filters, and our pushed filters are going to be applied in that order. One thing to keep in mind, though, too, is that our timestamp and string values or data values for those specific types of columns aren't always going to be useful because you might have precision or truncation issues which are going to prevent exact matches, and you'll have to fall back to the file information sometimes. You'll also want to avoid collecting stats on any long strings or columns that may contain long strings. We want to put them outside that first 32 columns, or we can also just change the defaults, the data skipping number of index columns, to exclude any of those columns that may contain long strings. Now, what about partitioning? Partitioning is classic, right? We can avoid scanning through data files if we partition for specific columns. Databricks says, let's not do that, because it's so easy to accidentally cause the tiny file problem, the small file problem, or to accidentally skew our data. It's very often misused, it's overused. We're going to talk about in a demo how this can take place, even inadvertently doing this. So Databricks does not generally recommend it. However, there are some use cases for when you might want to partition data. For example, if you want to isolate data for separate schemas, right? Single to multiplexing. Or if you have GDPR or CCP use cases where you're commonly going to delete entire partitions worth of data. That will take a lot less time if you've partitioned for that data. There are also use cases where you're requiring a physical boundary. If you're using SED type 2, you're partitioning on current or possibly not based for better performance. Now, if you're going to partition, choose a column that has low cardinality. High cardinality columns are going to cause smaller file sizes. Try to keep your partition less than 1 terabyte and greater than 1 gigabytes worth of data. If you're going to have tables that you're expecting to grow larger than terabytes, partitioning might be a good idea. You're partitioning usually on a date column. You may Z-order on commonly used predicates in where clauses as well. But again, liquid clustering is recommended. Here's the challenges with partitioning. You may end up with many small files, with high metadata operations overhead, and slow read operations, and you might end up with data skew where you have inconsistent file sizes across partitions, right? So you have one partition that has tiny amounts of data and other partitions or files because of the partitioning that have large amounts of data. That's going to lead to poor optimization. So liquid clustering, we've talked about it a few times. What is it? Liquid clustering is an innovative technique that Databricks has come up with to reduce data management and cause more support for efficient query access. And it's really a flexible and adaptive way that will change with your data and will scale very well and avoid data skew. With liquid clustering, you get clustering on, so you get the best performance right out of the box. It's immune to data skew and allows for more consistent data skipping. You have minimum write amplification on table maintenance, which is a true incremental optimize, row-level concurrency, which simplifies logic of concurrent writers, and reduced cognitive overhead. You don't have to worry about cardinality, high cardinality columns, low cardinality columns, whatever it might be. Liquid clustering is exactly what it means. It's liquid. It's adaptable to as your data changes. So with liquid clustering, we're essentially targeting a specific file size. And the liquid means that it's not subject to those rigid boundaries. We can intelligently decide what ranges of data to combine to make file sizes roughly the same size. Therefore, we reduce data skew to a point where it's basically gone. We have data sizes that are consistent. And liquid stores metadata now, and that metadata then can be used to cluster into existing clusters on write. It makes writes faster and definitely makes reads faster as well. There's table statistics that are going to be calculated for any of these techniques as well. As we collect these statistics on these columns, we're going to increase the optimization of the tables as we read through the data files associated with those tables. It's going to help with AQE, or adaptive query execution. We're going to be able to ensure that we choose the proper join type through that AQE. AQE is going to select the correct build side in a hash join. It's going to calibrate the join order in a multi-way join as well by the calculation of these statistics. We can run these statistics and analyze by issuing a command, analyze table, give the table name, then we say compute statistics for all columns, and those statistics are going to be calculated. Now, Databricks has also introduced predictive optimization. And what predictive optimization does is it uses predictive analytics techniques to automatically optimize and enhance the performance of systems, processes, or workflow. It involves leveraging data-driven insights to proactively identify and implement optimizations, which improves efficiency, cost-effectiveness, and overall system performance. Effectively, what predictive optimization does is you allow Databricks to look at your usage patterns and determine what predictive optimization techniques can be implemented to get the best value and the most optimization, basically the best bang for your buck. Predictive optimization has these features: automatic maintenance, right? You don't have to worry about your optimization anymore. There's automation that executes in the background maintenance tasks that you used to have to worry about. And again, only on Delta tables. It supports maintenance operations, things like optimize and vacuum. These things that you used to have to worry about in the past are now automated. You don't have to worry about them anymore. Basically, you set things, you forget about it because it's intelligent, and it will automatically run these maintenance jobs without you having to supervise them. And it also implements serverless computing, which makes it so that you no longer have to manually manage compute clusters. Predictive optimization takes care of all of it for you.